Hello, I'm Michael O'Connell, and in today's video, we are going to be using the Crank-Nicholson method to address the problem of stability we encountered in the previous video. The Crank-Nicholson method is an implicit differencing method. So, on the board here, I have the beginnings of the explicit differencing method we have been using, which we saw in the last video has problems of stability when the time step is greater than 0.5 seconds. Now, specifically, that would have been our R value being greater than 0.5. That is what caused the problems of stability. With the implicit differencing method that Crank-Nicholson proposed, we will be taking a different approximation of the second derivative of the temperature with respect to position, where we actually use the temperature values at the next time step as well in this approximation. And what we're going to be doing is actually taking an average of the temperatures at the next time step and the temperatures at the current time step. So let's take a look at what that would look like here. I took some time to rewrite the equation that I had on the board so that we have more room to work here. What we want to do is find the temperatures at the next time step n+1. So we want to isolate those on one side of the equation. We're going to begin by doing something we did in the explicit differencing method where we combine certain constants. So these are going to be the same type of constants once again. We have alpha, the thermal diffusivity. We have a delta x squared that we can pull out. Once again, that's in the denominator of both of these terms. That stays in the denominator. And then we can multiply both sides by delta t, so that will go in the numerator. So we have this term here, okay? And don't forget the 2, because again, we're taking the average. So this, you might remember, would be r over 2, but when we code this out in Python, we'll denote this as u, okay? I'm so used to writing u, but it's going to be u. Now, that is going to be important for us. Now, I'm going to isolate all of these temperatures at the next time step n+1 on the left-hand side, and then the temperatures at the current time step n on the right-hand side. So just watch me carefully as I do that real quick. And remember that we have this new constant now. I'm going to erase these, actually, so that you don't get confused. These can all go away, because they're all represented right here as u. Okay, so be careful, because this has to be multiplied on each of these terms. So just watch closely, and I will try to be as careful as I can to not make a mistake. Okay. This equation differs substantially from what we had before with the explicit differencing method, because now we have multiple temperature terms at the later time step n+1 that need to be calculated. How are we going to do this since they depend on one another and are at different positions? To do this, we need to recall that the number of unknowns we have depends on the number of position increments we divide our bar into. So if we look at our bar, of course, we need to remember that here at the left boundary, the temperature is known, and at the right boundary, the temperature is also known. And then we have all these position steps in between. Okay, let's say we divide up the bar into n increments, okay, and we start at 0 at the left boundary. Then the temperatures at all of these internal position steps, these are unknowns, so we'll need an equivalent number of equations, which means we will be using matrix multiplication to solve this. Now, this temperature is known and this temperature is known. We have n number of position steps. So each time we jump to a later time step, we will need to solve n-2 equations for n-2 unknowns, our internal temperatures. Okay? And then we're going to plot those for each later time step, okay, to get those beautiful plots, and that will be our temperature profile. And the goal of this is to get a solution that is actually stable. That's what the Crank-Nicholson method is all about. Now, I'm going to have to erase a lot to give us some space so we can go through the matrix multiplication, and then we will implement that in Python and make beautiful plots. Let's use matrix multiplication to describe our equation up above. Let's begin by writing out the vector of unknown internal temperature values at the later time step in +1. So the first internal temperature value we will have is going to be one position increment to the right of the left boundary, which would be T sub 1. Then the last unknown internal temperature value will be one position increment to the left of the right boundary, which would be T sub n minus 1. Okay? And we have all of these internal temperature values in between here. Okay? Now let's start performing the matrix multiplication to describe the left-hand side of our equation. Remember that this is going to be done row by column, of course. Okay, so if we begin with j equals 2, our first term there is negative u multiplied by j minus 1, which is 2 minus 1, so multiplied by t sub 1. Okay, so that will correspond, of course, to column 1 here, but we, of course, are in the second row of our matrix over on this side, so this is going to be negative u, okay? And then the next term is going to be 1 plus 2u, and that is multiplied by t sub 2, of course. And then we have minus u multiplied by t sub 3 there, okay? Now, we are going to have a pattern here, because when we are at t sub 3, we have minus u multiplied by t sub 2, so that would go right here in the second column. Then t sub 3 multiplied by 1 plus 2u again. And then for t sub 4, we would have minus u right here. I'm kind of out of room, but you get the idea. Now, for t sub 1, what would we have there? Well, here you would have the 1 plus 2u up in the first column. And then for t sub 2, second column, you have the minus u, okay? And let's look at what we would have for t sub 4 here in the third column. That would be, of course, another minus u. Now, obviously, there is a pattern going on here. This is called a tridiagonal matrix. We are going to use a very special method in Python to solve this, okay, so that we can get at these unknown internal temperature values for each time step that we take, so that we can make our plots for the temperature profile of the bar. Okay, so this is excellent. We have the left-hand side of our equation described very well. Now, we are going to have a vector of known values based on these these will be internal temperatures because we have these internal temperatures here, okay? Most of them at least. But again, these are known temperature values at the current time step n, okay? Let's begin once again with t sub 2. And notice that I don't need to worry about the order because this is an actual matrix. This is just a vector of known values. So I don't have to worry about the order in which I write these terms because we're not doing any sort of matrix multiplication over on this right-hand side. So this is j equals 2, which corresponds to t sub 3, and that's multiplied by u, okay? So let's just begin on that side of the equation and keep our order as we do this. So this would be u t sub 3, 1 minus 2u here. Notice that I keep the equation because it's all known. It's all at the current time step n, multiplied by t sub 2, and then plus u multiplied by t sub 1. If we did this for t sub 3, we would follow a similar pattern, right? We would just be increasing our time step by 1, okay? So this would look like this. Okay, notice we just increase each of these values, okay? And this would go all the way down. Now, at this term and this term, we have something different, okay? Let's begin like we normally would. Let's just start with this equation, okay? So we're going back to t sub 1, so we just drop the time increment here, here, and here, of course. So this is u times t sub 2 plus 1 minus 2u t sub 1 plus u multiplied by t sub 0. Likewise, over here, we would have u times t sub n plus 1 minus 2u t sub n minus 1 plus u times t n minus 2. Okay, what do I want to call your attention to here? For these two terms, these two internal temperatures, we actually need to consider the left-hand side Because here, for this internal temperature, we have also another J minus 1 term here, okay, where we get T sub 0. T sub 0 is extremely important because that is the temperature at the left boundary that stays constant. So when we move to the next time step, n plus 1, the value is still the same, and it's something that we know. So we don't want that incorporated with this matrix multiplication on the left-hand side at the current time step n plus 1, where we're trying to find internal temperature values that we don't know, of course. We don't want that over there. So we're going to add this to the other side and incorporate it in our vector of known values. So let's combine like terms. So we have u times another t sub j minus 1. So that's where this is going to be added. Remember that our j value is 1, so this is t sub 0. We already have u times t sub 0, and we're just going to add another one, okay? We're going to add this to both sides. So that makes that work, and we're going to have 2u times t sub 0. Something similar happens here at t sub n minus 1. Here, we have this position increment j plus 1, okay? So n minus 1 plus 1 is n. T sub n is very important once again because that's the right boundary temperature, which we also know. So we don't want that on the left-hand side of our equation. So we're going to add that once again. This is a negative u, so we're going to add it to the other side of the equation. And again, that's going to be at t sub n. So instead of u times t sub n, we're going to have 2u times t sub n. And that basically completes this part of the video where we're on the whiteboard, because now we are going to implement this matrix multiplication that we are performing with the tridiagonal matrix in Python. And this will allow us to make those plots for all the time steps that we want, okay? And that is going to be the temperature profile. Obviously, the key difference in this video is that we have implemented the Crank-Nicholson method, which is an implicit differencing method. The goal here is to get a solution which has the temperature profile of our bar, of course, but one that is stable for any time increment that we want to use. Of course, where we're keeping our thermal diffusivity and our position increment at the same value. Okay, if you remember from the previous video, our time increment was limited to 0.5 seconds at the largest value. And we may want larger time increments to save ourselves computing time. Okay, now obviously when you increase your time increment, although your solution may be stable because you're using the Crank-Nicholson method, it may be less accurate, okay? So we'll talk a little bit more about that when we make the plots in Python, but that is what we are going to do. I'm going to erase all of this and we will head over and code this up. Now we're ready to implement the Crank-Nicholson method to obtain a temperature profile for our bar. Now, we are going to use a SciPy algorithm that is designed to solve problems with banded matrices. Our matrix has 3 diagonals of non-zero values. Those diagonals are the bands we have. So we have some indexing to consider based on the information I have on the screen. So what would this value be? This is row 0 for Python indexing, and column 1. For us, from what we had on the whiteboard, that would be this value here, minus u. And notice we go to row 1, column 2, and down along the line through the diagonal. The next diagonal is what we call the main diagonal, and that incorporates all the columns, okay, through that entire diagonal. As you saw over here, that's the 1 plus 2u, okay? So we want to implement this in our Python code. And we can start with a matrix full of zeros, of course, and then assign the values for each diagonal. So let's start with that. Now, I copied and pasted everything we had from the previous video. We can make some slight adjustments. Let's put in u, okay? And this term, of course, will be divided by 2, okay? So we're ready to go. Now, let's begin with matrix A, and we'll use numpy zeros. So what size do we want to have here? Well, we have 3 diagonals, so that's the number of rows. And then we have the number of columns, which is based on the number of internal temperature values, which of course depends on how we divide up our bar. How many position increments do we have? We have n increments, so 20. So it's going to be n minus 2.
we subtract 2 because we have the temperature defined as constant 50 degrees Celsius at the left boundary and then 80 degrees Celsius at the right boundary. So that is the reason for that. Now, let's take a look at the indexing that we need to consider when we assign values for each diagonal. To assign the non-zero values for the diagonals, we need to do some slicing. So our first diagonal will be negative u. Our second diagonal will be 1 plus 2 times u. And then our last diagonal will be negative u as well. So how are we going to slice this up? Remember, this matrix is our banded matrix, okay? It is 3 rows because we have 3 diagonals. So when we begin these slices, it starts off easy, right? Because this will be row 1, which, of course, Python indexing begins at 0. So that's going to be row 0. This is going to be row 1, and then we have row 2. And then we'll need commas. What we have to slice here are the columns, okay? Because some of these are empty, right? This is empty. There's just an asterisk. This is empty. There's another asterisk. So we don't want to put anything there that doesn't belong there. And we see that, of course, in our matrix here, right? There's nothing up here, and then there's nothing down here, okay? This is a little easier because we just have these 3 diagonals with our main diagonal in the middle. So how are we going to describe our first diagonal, the upper diagonal? Well, of course, we start with row 0, but we're in column 1, and we go all the way to the end. So we do 1 and then colon, okay? What about this one? This is just a colon. It's easy because it's the main diagonal, and it incorporates all of those columns, so you just denote that with a colon. The last one, we need to exclude the last value. So we do that by starting with a colon because we start at the beginning over here. But then we omit this last value. So to do that, we just do negative 1. Negative 1 is the last value, but that's not included in the slicing. So now we've described our banded matrix and we've implemented it into our code, and we are ready to continue. Now we need to use our for loop to calculate all of the new temperature values for the internal position increments. To do this, we want to use our equation, and we want to describe the answer, the right-hand side of our equation. This vector needs to be in our for loop. That way, each time we go through our loop, we calculate these new temperature values for all of the internal position increments. Now, we already have a vector array for the temperature values for our bar at time is equal to 0. So this becomes quite easy. We just have to slice that up. So what will we use for this? Well, we will follow the equation. So we have u times t, and this goes from 2 all the way to the n. And again, these indices and these slices are describing the position increments. And let me show you that here in Microsoft Word. So we go from 2 all the way to n. Then we go from 1 all the way to the second to last value, okay? So here we're going to have 1 minus, and then this will be 2 times u, okay? Multiply this by t, and then our slice will be 1 to negative 1. Again, we don't include this last value that describes, okay? So that works out nicely. Let's copy and paste this, and we will use a different slice, of course. So here we have the same thing, and then we go from 0. So we start at 0 and we go to negative 2, okay? Now we have to deal with this. So we have 2u times t sub 0 and then 2u times t sub n. Okay, so how do we deal with that? Well, we will just append those. So we have b0 equals b0. And don't forget the u here. That's kind of easy to forget, but it's u times t. Now we just need to copy and paste here so we can append the last value. So we will just change all of these indices to negative 1. Okay. Let's adjust some things here. Let's make this every 50, and we'll make this 500 even numbers. Okay. And then we will get rid of this. And now we can implement solve banded to see if this works. I've copied and pasted code here so that we can test our solution using solve banded. So let's do that now. And I have to put this up above as well, okay? And really, we're just interested in the parameters that we will need to supply. So this will be from scipy.linalg. It's for linear algebra. Import solve banded. Okay. Let's make a couple of adjustments because we are looking for a solution that's stable with a time increment that is greater than it was before. So it's greater than 0.5. So we'll do 1 second for that. Let's increase our starting temperature to 25 just to switch things up a little bit. Okay. What do we have to supply here? The first thing we have to supply are the number of non-zero lower and upper diagonals. So lower, comma, upper. So we have one of each. That's easy. And then we have our banded matrix and the right-hand side. So A, comma, B. That's pretty easy as well. And look at that. Okay. So these are the new temperature values for the internal position increments. So now we can implement this in the for loop and get the temperature profile for our bar. Let's implement our solution. So I just got rid of all the code that I had before. Now we need to set this equal to the internal position increments. So now we have solve banded once again with everything in it. Okay. And we should get a nice temperature profile, and that's exactly what we get. So this is the solution that we have here. Okay. And I think it looks great. What is great about this is that we used the Crank-Nicholson method, which is an implicit differencing method, and we obtained another temperature profile for this bar. It's the same situation. However, this time we used a larger time increment and our solution is stable. Now recall what we had previously. If we did a 1 second time increment, we got something like this, which is an absolute disaster. Okay. So in the next video, we will demonstrate how this method of implicit differencing is stable no matter what time increment we choose, which is extremely amazing. However, we do have to remember that the larger your time increment, the less accurate your temperature values are at each position increment, because you are plotting the temperature versus position. So the larger increments you take, you are making less accurate approximations, right? Because you might have some sort of curve going on and you're approximating it as just a linear straight line, right? For that delta t, because that's your time increment. So that is something you would have to consider when you're doing these computations. However, it's amazing that we have the Crank-Nicholson method that is stable for any time increment we choose. Really, it's for any value of u that we have. Okay, so in the next video, if you want to watch that, it will be very cool. We show how that is actually the case using the von Neumann stability analysis once again. So thank you so much for watching this video, and I hope to see you next time.